Hello and welcome to Empowered Learning. This particular video will be about limits, but we're going to study limits from an empirical standpoint, meaning that we're going to look at limits graphically. We're going to look at an informal, as I like to call it, layman's version or definition of a limit, because we won't be studying the precise definition of a limit in this video. And if you don't know what the precise definition of a limit is, that is the definition of a limit with the epsilon and deltas in the definition. So we won't be taking that approach here. But the main thing here is to kind of get an idea of what's going on from an empirical standpoint when we talk about the behavior of some function. And so this video will be a little bit more computational than the other video that I did on limits, where we were just simply looking at graphs and taking it from a holistic approach. If you have not watched my first video on limits, which I call a primer on limits, you want to look up that video and check it out before you watch this one. Because if you do that, you'll have a more intuitive understanding of what's going on as we do this particular video. This video I'm doing because most calculus textbooks, when they start to talk about the definition of a limit, they do it from this perspective. And so it's not necessarily my favorite perspective to start from, but I do understand that students are looking for material to be able to understand what's going on from that approach. So I'm making a video to satisfy that need. All right. We're also going to look at some functions once we get done with this whole basic study of limits. We're going to look at some functions, and the purpose of that is for us to study some limitations that technology has. So I know a lot of times we're asked to graph things on graphing calculators and or in Desmos, and a lot of times that's fine. But when we're talking about limits, there are some functions to where it just doesn't work out well, and we have to do this thing called think to figure out what the limit of that particular function is. So in that sense, we're going to culminate this particular video talking about those topics. All right, so let's get started here. So the definition of a limit, and I'm calling this the layman's version, again, because it's an informal definition. We write, and I'm saying it that way because this is really notation that we're using here, because we're really introducing this limit operator, because there's a lot going on when we say we're taking the limit of a function. But this is the notation for it. LIM as x approaches some number a, and of course we need to always say what we're trying to take the limit of, some function, and it's going to equal some number L here. Okay, we write and say that the limit of f of x as x approaches a equals L. Okay, and if we make the values of f of x arbitrarily close to L, meaning that the closer and closer we get to this real number value L, we're doing that by taking the x values. Of course, you see how x approaches a here. We're taking x to be sufficiently close to a. So on either side of a, but not equal to a. So in other words, what I'm saying here is that if my y values are within, let's say, half a unit from what L is supposed to be, then if the limit of this particular function exists as x approaches a, then if I'm half a unit away on either side from L here, then I may be 2/10 of a unit away from a here. Okay. And if I go in a little further and I say, all right, for my y values, if I am 0.1 of a unit away from L here, then it means I may be 0.001 away from a here. Okay, so that's essentially what this informal definition of a limit is trying to say. Now, we have an alternative notation for this particular way that we express a limit, and we normally will write it as a function approaches this real number value L as x approaches this real number value a. Okay. Now, when we go over limit laws, we will discuss some basic properties of limits when evaluating the limit of a function at x equals a. And these properties will help give us a shortcut to evaluating these limits in the future. Okay. And so I'm actually going to record another video on limit laws separately from this one. So watch out for that one as well. For now, we will need to first empirically evaluate the limit of several functions in order to get a feel for how to correctly go about investigating the behavior of a function when evaluating a limit. We also want to expose some common mistakes made when evaluating the limit of a function by using calculators to help investigate function behavior. Now, the main point that I want to get across here before we move on, and this is really the main point of the other limit video that I talked about, the primer on limits, is that when we use this operator here, we know that limit is equivalent to behavior, okay? Or when we say limit, what we should be thinking about is behavior. And so limit is really just a fancy way of saying, hey, I want to study the behavior of a function as it approaches some particular x value. Okay, that's really all it is. All right, so now we'll go ahead and investigate the concept of a limit by first looking at the difference between secant and tangent lines and what info they possess for some function f of x here. Okay, now when most calculus students, first year calculus students, talk about tangent lines and secant lines and all of that, it's usually to eventually get to the point to where you're going to start talking about the definition of a derivative. If you're watching this video, then you're probably not at that point yet in your course, because there's a few other things that we have to sort of establish before we can actually start talking about the definition of a derivative as it's expressed in terms of limits. So what we're going to be doing here is looking at what a tangent line versus a secant line is, really from an empirical standpoint. And I'm going to try to use graphs to be able to sort of get you in the right mind frame as far as what you may think a tangent line is and what it is a tangent line actually is supposed to be. And of course, that's going to help us to eventually get to a point where we'll start talking about the definition of a derivative in later videos. All right, so first things first, when we talk about a secant line is a line that intersects a curve at exactly one point, okay? So an informal definition of a tangent line is a line that intersects a curve at exactly 2 points. However, what I've said here is really a crude definition of what a tangent line is supposed to be, and it does not hold in all cases. Now, the reason why it doesn't hold in all cases is because it's a very loose definition, okay? And that's part of the reason why in calculus, one of the main destination concepts in the course is to properly define what you mean when you say a derivative. And in order to do that, we have to properly define what it means when we say a limit of a function. So that's really the whole purpose of this. Now let's take a look at these graphs here. Now, when you first probably heard about a tangent line, it may have been when you were in grade school and you're studying physical science and you heard about this concept called centripetal force. And a simple way to describe centripetal force, think about having a string tied on to a weight and you spin the weight around in the air. And if you wanted to figure out, well, you know, how fast is that particular weight traveling in the air at any given instant, if you would take a snapshot of you twirling the weight around with that string, then of course, based upon how long the string was, would kind of give us an idea on the velocity of that particular weight as you spin it. okay? Provided that you're spinning it with the same kind of force. And so here we would say that, hey, if I want to know how fast it's going, or another way to say what's the force acting on that particular point here, then the centripetal force would be the force that is acting, as we call it, tangentially off of this particular circle at this particular point, okay? Now, if we were to characterize the corresponding line that goes through this particular point here, what we would call that is a tangent line. Okay, and that's what we mean when we intersect a curve, and our curve this time is a circle and intersects it at exactly one point. Okay, now figure 2 here gives an example of what we call a secant line as well as a tangent line. Okay, so as you can see here, our secant line is this line here, and we see how it takes this curve here, which is a parabola, and it intersects it at exactly 2 points. We also see here that we have a tangent line. And so and I'll go ahead and draw it first. So this is tangent line. And so what this tangent line is supposed to do is intersect our curve, which is a parabola this time, at exactly 1 point. And that 1 point would be here. Okay. Now, what a secant line is and what a tangent line is and what it's really supposed to be, figure 2 is sort of capturing what that's supposed to look like in an actual practical example. If we look at figure 3 here, we'll see that, again, we have secant line. Okay, it's following what it's supposed to do here. But unfortunately for the tangent line, if we use our definition of we intersect a curve at exactly 1 point, by the definition that I gave, this is a tangent line. However, it's not what we really mean when we talk about a tangent line. Okay. The difference is in the tangent line here, do you notice how the slope of this particular line is negative? So that means that it's going down or decreasing. And also notice that my actual function is decreasing as well. Okay. And so what tangent lines are supposed to do is not only intersect a curve at exactly 1 point, but it's supposed to also indirectly describe whether the curve that you're dealing with is either increasing, decreasing, or constant at that particular point as well. And so this is part of the reason why we have to kind of come back and clean up what it means when we say we have a tangent line or a secant line. Okay, and particularly for a tangent line, we have to clean that up, and we use limits to be able to do that. Okay, now when we talk about a tangent line and we eventually define what that means in terms of limits, it's going to mimic more of what we're talking about here. Okay, but I wanted to show these graphs first, just so that you have an idea of what you were probably told before, the kind of way that we're going to think about secant lines and tangent lines now, and how limits actually fit into that. Okay, so we're going to look at an example now where we're actually going to find the equation of a tangent line, and we're going to do it by looking at a function. In this case, it will just be x cubed, and we're going to find out what the equation of the tangent line is going to be at the point 2, 8 on its graph. Now, the approach that we're going to take here is we're going to look at things empirically, okay? Meaning that we're going to try to figure out what the slope of the tangent line is by first looking at what the slope of the secant line could be for several different points on this particular graph. And eventually what we're going to do is try to take our secant line, and as we get closer and closer to the point 2, 8, our secant line is going to morph into a tangent line. Okay, and so we're going to do some calculations, and we're going to see how, by calculating the slope of a secant line, how we keep doing it as we get closer and closer to that 0.28, that it eventually ends up being a tangent line, and we'll be able to find the equation of the tangent line by figuring out the slope of that particular line, okay? Because that's the main thing that we need to know. In order to find the equation of any line, of course, we need the slope and we need a point, or we need 2 points, okay? And in this case, since we're already given the point, our main goal here is to find out what the slope of this particular line is, or the slope of this line T that we're talking about here. All right, so let's go ahead and get started with this example here. So in order to find the slope of a line, we need the slope of the line and at least 1 point. So to find the slope M of this line, we'll first look at the slope of a secant line between some arbitrary point, which is going to be x cubed. And remember, this is just another way of saying x, y, where y is equal to x cubed, and the given point 2, 8, or in this case, 2 and f of 2, because if I plug in 2 into x cubed, 2 cubed is 8. Now, to do that, to form the slope of the secant line, notice that this particular formula looks very familiar. It's just the slope of a line in general, okay? Now, what I have here is actually what's called the difference quotient, okay? And this is a very fancy way of expressing the slope of a line. And to be specific about it, if I looked at the slope of my secant line, and the 2 points that I use would be a point x, f of x, as the first point, and the second point, I said, hey, let me go h units away from here, and then I plug in that x value to get the corresponding y value. I would have this. And now, if I wanted to label these as x1, y1, and x2, y2, if I put it back into this formula here, I would see that y2 would just be f of x plus h, where the x plus h is all on the inside. The y1 is just f of x. And of course, the x2 minus x1 would just be h, because x2 minus x1, these x's here, they cancel to 0, and all you have left is h. So difference quotient, this is something that you may have learned in pre-calculus. This is another fancy way of expressing the slope of a secant line. Okay? Now, what we're going to do with this is we're basically going to form the formula for the slope of the secant line, or just the slope of a line that's connected to this particular function here. And so in terms of this difference quotient here, what we're actually doing is we're looking at it this way. And just so that you know, it's not in this same form, but this is another form of a difference quotient, okay? And I'll come over here, because we can also express a difference quotient in this way, okay? And it all really is just depending upon how you want to express the points to find out your slope of the line, okay? Now, in this case here, the points that you're looking at are a, f of a as the first point, and the second point will be x cubed for this particular example. So that's how we formed this particular formula for the slope of the secant line for our function y is equal to x cubed, and All the action is, of course, around the 0.28. So what we're going to do now is we're actually going to figure out for several different values of x what this result is going to end up looking like here. Okay. And so we're going to use this chart to be able to help us out here. Now, to help us to be able to calculate this, I'm going to use a graphing calculator and put this particular formula in it, and then let it give me all the different values. All right, so we're going to go ahead and put in that secant line formula, x cubed minus 8 divided by x minus 2. So I'm going to come here and actually just type that in. So I'll have this and then x cubed and then minus 8, and we'll divide all that by x minus 2. Okay. And so once I do this, I'm going to check my window and everything's going to be fine there. The main thing that I'm concerned about here is just finding what are the corresponding y values, which would be the slope of the secant line here based upon the x. Now, some people like to actually go in and look at their table or whatnot. I'm going to use the calculator feature here to be able to do that. So I'm going to go to secant trace, and that's going to do calculate. I'm going to calculate a value. It'll go ahead and graph the function or whatnot. Hadn't done it, but that's fine. What I really care about here is just evaluating. So according to that list, if I look at x as it approaches 2 from the right, I'm going to start off with the number 3. I'm 1 unit away. Figure out what that value is. And so if I do that, when x is 3, that's going to be 19. If I go down to 2.5, then we see that's 15.25. If I go down to 2.1, and notice what I'm doing is from 3, I'm trying to get closer and closer to 2. I get to 12.6. Get a little bit closer to 2. I get to 12.006001. And if I do it one more time, then notice here that it seems like as x approaches 2 from the right side, I'm getting closer and closer to 12, meaning that my slope of the secant line is approaching a value of 12 here. Okay. Now, if I did the same thing coming from the left side, I'm going to start 1 unit out from that, which will just be 1. So of course, when x is 1, slope of the secant line is 7. And it's 1.5. You see it's 9.25. 1.9. You see that is 11.41. 1.999. 11.994001. And then we'll do 1.5 nines. And you see how on the other side, it's starting to get a little closer to 12 on the other end. We could go a little bit more. All these nines. And you see that technically it gets to 12 just because it's not actually there at 12. But what's happening here is that once I go, beyond so many nines here, the calculator is just truncating all this and saying, all right, well, that's the same thing as 2. Okay. So that's essentially what's going on. Okay. Now, part of the reason why I'm saying that in this case, if I do all these nines here, the calculator is just truncating the 12 is because if we go back and look at this, if I plug in 2 right here, I technically have 0 divided by 0 here. And of course, 0 divided by 0 is not a defined number. So it can't do this. And so this is part of what I meant when I was saying that your calculators have, depending upon what you use, they have some limitations because here, what this is actually showing you, it's not really showing you what it should be showing, right? Because when x is 2 here, this should say undefined, but it's not actually saying it, okay? All right, so let's go back and fill in our tables here, and then, of course, our conclusion here is that the slope of the secant line, as it gets closer and closer to 2, coming from both the left and the right, the behavior of what's going on is acting the same, okay? And we see that from either side, it looks like the slope of our secant line is approaching 12 as x gets closer and closer to 2. So we're going to fill all that in and move forward. All right, so now that we've used our graphing calculator to get these values here, we're seeing that as x approaches 2 for this formula for the slope of the secant line, as x approaches 2 from the right and from the left here, we see that it seems like the slope of the secant line is trying to converge upon this value of 12. So as x approaches 2 from both the left and the right, slope of the secant line seems to be approaching 12. Now note the tables that we did previously as x approaches 2 from both the left and the right was showing that the slope of the secant line changes as our point x cubed changes, okay? That is to say the behavior of the slope of the secant line changes as this changes. Now the behavior of the slope of the secant line as x approaches 2 from either side acts like it is approaching the same number of 12. The behavior of the slope of the secant line as x is limited to approaching x equals 2 is called the slope of the tangent line, okay? So here, my point is that the slope of the secant line as x gets closer and closer to 2, it's going to morph into what we call the slope of the tangent line, okay? And so here we know that the slope of the tangent line will be the behavior of the slope of the secant line as x approaches a from either side of a, okay? And so for here, we see that from what we've seen empirically, and empirically just means that we've kind of observed what has gone on by our calculations and whatnot. We see that the slope of the tangent line here should be 12, okay? So now we want to find the equation of the tangent line when the slope of the tangent line is 12 and we have this point. Now, of course, if we have that, then life is easy because now we're back in elementary algebra where we can use our point slope formula to be able to find out the equation of the line, where our x1 and y1 is the x and y coordinates 2 and 8. And then, of course, the slope here, m, is going to be 12. And we just need to solve that for y. So I'll just go ahead and do that really quick here. Of course, if we add 8 to both sides, I'll also distribute this. This would be 12x minus 24 plus 8. And y is just 12x minus 16. And so what this means now, I'm going to go back a page here, is that this particular line that we were talking about here, line T, the slope of that line is going to be 12. The equation of this line is going to be 12x, y equals 12x minus 16. All right, so now to kind of summarize what we've done here in general, we say in calculus, the way that we describe behavior of a function as x approaches a, where a is a member of or belongs to the real number set, from either side of a, meaning coming from the left side of A or from the right side of A is as this particular notation here, okay? And so remember, limit just means what? Behavior, that's right. So from our previous example, we could say that the slope of the tangent line is going to be the limit of the slope of the secant line as x approaches 2, in this case, from both the left and the right. And of course, our formula for our slope of the secant line was this, and we saw that empirically that equaled 12. Now, attention, we know that the slope of the secant line, another way that we've called this concept is just average rate of change, okay? So if I want to know the average rate of change of something in between one value to another value, essentially what we're saying that we want is the slope of a secant line. And to make it even more simple, whenever we talk about the slope of a line in general, if that line is going through some other curve or other function, then at that point it's technically called a secant line, okay? Now, whenever we talk about the slope of a tangent line, it's no longer average rate of change. It's actually called instantaneous rate of change, okay? And I'm going to go back to our graph of the last example to explain why we call it instantaneous rate of change. Now, if we look at this tangent line here, notice that this line is going through this single point right here. And so whenever we try to figure out what is going to be the slope of the tangent line, what we're saying is that at this particular single point here on the graph of this function, x cubed, we want to know how fast is that particular function increasing at the moment that it is at the point 2, 8. So if you can imagine like a particle or a person, and this is a roller coaster, and the I guess the motion path here is a lot like x cubed. If they start from down here, then at the moment that they get to this point here, we're really asking, well, how fast is this particular function increasing here? Well, or how fast is the function changing at this point here? Well, it's instantaneously changing at a rate of 12, okay? So change in y values to change in x values at this particular point in that instant or snapshot in time is going to be 12, okay? Now, if I wanted to know what that was, let's say here, then of course, notice how our function flattens out here. And if I was to actually try to figure out what it is there, then of course, the slope of any horizontal line is 0. So the slope of the tangent line at this particular point here would be 0. Now, and of course, I could go through this whole process again, and instead of using the point 2, 8, I could use 0, 0, go through the whole process, and I could show you that as x approaches 0 coming from the left side and from the right, that the instantaneous rate of change or slope of the tangent line would actually end up being 0. So now at this point in our study of limits, what we're going to do is take a look at the graph of several functions. Some of these functions you could probably draw by hand if you remember your translation theorems or transformation theorems from pre-cal. Some of these others, some others may be a little harder to draw. So what I'm going to do is I'm going to use a combination of either Desmos or the graphing calculator emulator that I had that you saw earlier. We're going to use a combination of those two things to be able to do this particular exercise. The main point of this exercise is to give you some insight on what your calculators can do and what they cannot do in helping you to be able to evaluate the limit of a function, okay? And I stressed this in the primer on limits video that I made, and I want to stress it here as well. One of the key things that you need to be able to do whenever we are dealing with evaluating limits is you need to remember what the graphs of your basic functions look like. And what I mean by basic is all of your algebraic functions like y equals x, any horizontal line, y equals a number, x cubed, x squared, square root of x, absolute value of x, cube root of x, 1 over x, 1 over x squared, your integer, or I like to call it stair-step function, basic exponentials, basic logarithmic functions, all those things, you need to know what they look like, okay? Also, your trigonometric functions as well, all your basic trig functions, sine, cosine, tangent, cosecant, secant, cotangent, and it's also helpful to be able to know what the inverse trig functions are. So your sine inverse or arc sine, arc cosine, so on and so forth. Okay. I highly recommend that you commit those graphs to memory, or at least know how to be able to produce those graphs from memory. Okay. Now I'm saying all that because in this whole study of evaluating limits, there comes a point in time, even, of course, we're doing all this empirical stuff, and then the limits primer that I did, the video that I did earlier for that, it just really boils down to sometimes you just have to know what the graph of that function looks like, okay? And there's really no substitute for it. We're going to learn other ways as you go throughout your first year calculus course. We're going to learn ways to be able to computationally evaluate limits, but really at the end of the day, even in doing all that, we're still going to face situations where we're just going to have to know what the graphs of these functions are. And normally when we have those situations, we have to know what the graphs of what our basic functions that I just mentioned look like to be able to describe the behavior. All right, so kind of did my preaching on that. I'm going to move on. So what we're going to do here is look at each of these graphs, and we're going to study what is the limit or the behavior of these functions as they approach the x values that we're telling it to approach. Okay. And so we'll go ahead and start with this first one here. And I'm going to kind of switch views here, and we're going to look at Desmos here and just look at each of these and see what Desmos could do for us. If Desmos doesn't help us out, then we'll try to look at our graphing calculator, figure out, see if that helps. If that doesn't help, then we'll find other ways to kind of think about what we're doing here to figure out what these limits are. All right, so I've taken the time to type in most of these functions that we're going to have here into Desmos. So I'm just going to start with the first one. So, of course, we have this graph here, but it's not in the viewing window that we need to see it in. So I'm going to put it in the suggested viewing window that's going to help us to be able to see what this graph looks like just in general. And then we're going to see what the actual limit of it is. So I'm going to come here and I'm going to set this, and let's do the x min to 5, our x max. We'll allow that to be 20. And then our y min here, just do this from -1 to 1. And this should get us in the viewing window that we need to be in. Okay, so this is the viewing window that gives us a good idea what this function is like. If we're going to find out what the limit of this particular function is as x approaches 0, notice this is where x approaches 0 is, and we're going to look at it from both the left and the right hand side. So if I click on this from the right, looks like I'm approaching that, and you see how it's undefined there. Well, notice here that we got, when we're kind of close to it, the y value is 2488. On this side, notice it's just above 0.25. So if we think about that, even though it's undefined there, the limit of this particular function here looks like it's actually approaching the value of 0.25 or 1/4. Okay. So you see how it could be doing that. Now, to make sure, we got 1, 2, 3, 4 divisions here. And of course, if we're going 0.1 of a unit here, this would be 0.2, 0.25, 0.3, 0.35, 0.4. So it does make sense that here at this hole in the graph, and it should be a hole there because when x is equal to 0, it makes our denominator 0, so it should be undefined. The limit of this actual function is going to be at 0.25. Okay, so we know that for this first function here, the limit of it is going to be at 0.25 or 1/4. All right, so let's look at the next graph. So the suggested window that I have for this one, I'm just going to do approximate values here. So that's approximately pi for the x min and x max. And then I'm going to go plus or minus 20 for the y min and y max. All right, so for this one, again, we're interested in knowing what the limit of this particular function is as x approaches 0 from both the left and the right. So if I come from the right, you'll see that it looks like this is getting closer and closer and closer to 1 on the right side. Again, I have a hole right at x equals 0, as it should be, because of course x is in my denominator. And if I plug in 0 for x for that, I get something divided by 0, which is undefined. If I look at it as x approaches 0 from the left, looks like I'm still approaching 1 as well. So here, and I want to show you this, do you see how here, how it's actually telling me that I'm already at 1? But technically this is telling me that at negative 0.016, I'm already at y equals 1, but I'm really not there yet. Okay, so what Desmos is doing here is it's saying that, hey, this value is so close to x equals 0 that we're just going to assume that it is 1, but it's really not 1 because, again, when we get to x equals 0, we know that it has to be undefined. Okay, so it's really not what they're trying to say here. It's really not that. If we actually plug in negative 0.03 and work it out for this particular function here, we're not going to get exactly 1. Okay, so you can see the limitations on the correctness of what a grapher like Desmos would do for you. But main thing here is that the limit of this particular function here is actually 1, because we see as x approaches 0 from both the right and from the left, the y values are getting closer and closer to 1. All right, so let's look at this next function here. And of course, we see that it kind of has this shape here. And as it gets closer and closer to 0, we see that it's just bouncing up and down an infinite amount of times. To give a better view of this, I'm going to adjust this, and let's say I'm going to just change this, the y min and y max here, and this is kind of a better idea of what's going on there. Matter of fact, yeah, and I'm going to adjust this just so that you can see it all. I'll make this a little more here just so that we can kind of see everything. All right. So the main point that I want to get here for this particular problem, if I'm taking the limit of sine of pi divided by x as x approaches 0, notice here that as we get closer and closer to 0 from both the left and the right, we have really no idea what's going on here, okay? And part of the reason for that is that for this pi divided by x part, the smaller the numbers x get, so when you get in between -1 and 1 for x, meaning like 0.5, 0.1, 0.01, the smaller the numbers are for x, the larger the result of pi divided by x is, okay? And so that's why you see the whole thing of you got, it really looks like it just shaded in, but what's really going on is that it's just oscillating back and forth so fast, because as these numbers for x get smaller and smaller, or should I say closer and closer to 0, the way in which the sine function oscillates back and forth is just getting bigger and bigger and bigger, okay? I could try to zoom in, but in zooming in, you see that Desmos is really not helping me out a whole lot, because I can just keep going and going and going and going, and you see that we're at a point to where Desmos can't even handle what's going on, okay? So here, even though we have a graphing calculator to try to help us out here, is really not helping us out enough. So we're going to have to do some thinking on our own, okay? Now, I could try to do the same thing using our TI 84, and I'll go ahead and switch views here and go ahead and do that. But what we're essentially are going to see is the same thing. All right, so we're going to do the same thing here. We're going to do sine of pi divided by x. And I'm going to go to my window here and put in the same suggested windows that I did for this other one. So this is going to be a minus pi. And for the x max, it's going to be pi. I will keep the x scale to be 1 for now, and we'll make the y min and y max 1 and -1 respectively. Okay, and then we'll graph, and you see that we have the situation here. Okay, now what I'm going to do is I'm going to switch this view a little bit, and I'm going to keep my y min and y max to be -1 and 1, but I'm going to decrease this x min and let it be -0.1, and let the x max be +0.1. And so do you notice here how our calculator, once it gets so close, is actually just saying that, hey, this is 0, okay? And then you can't really see this, but right there, it actually has a hole, okay? And so when a lot of students, when they first learn about limits and they take a function like this and they put it into their calculator, they assume that, hey, this thing is just going to 0, okay? Because this is what my calculator tells me. But that's not correct, okay? That's actually not happening at all, okay? The only reason why this is going to 0 is because the numbers here are getting so big that as x approaches 0 from both the left and the right, is getting, those numbers inside are changing too much, so it's just really just truncating everything to get to 0. So it's kind of like we're getting to some numbers here, like if we say sine of pi divided by point, and then you have like 20 zeros and then a 1, right? Then that's going to be sine of some big number here. But if that big number, if we look at it, since sine is a periodic function, if we take that and take out all the multiples of 2 pi, it may really just end up being something like sine of 0.0000000056254 whatever. And from a positive standpoint, that may look like it's approaching 0, but on the left side, the corresponding negative number, it's totally something different. Okay. So the point that I'm trying to get at here is that our calculators, all they do is they say, hey, you give me an X value, I'll give you a corresponding Y value. But because the calculators have only so much memory in it, it can't really think for you. Okay. Now, the answer to the limit for this particular function that we're dealing with here, it is actually does not exist. And what that actually means is that the behavior of this function as x approaches 0 from the left is acting different than the behavior of this function as x approaches 0 from the right. And I'm going to go back to our original view of the notes and explain why that actually is. All right, so at this point, I'm going to explain why the limit of this particular function here does not exist as x approaches 0 from both the left and the right. First, let's go ahead and put in what we know here so far. So we said that the limit for this is going to be 0.25 or 1/4. And we said the limit for this was going to be 1. So to deal with why this particular limit for this particular function here as x approaches 0 from both the left and the right does not exist. I'll go ahead and put that here. I'm going to go to another page here and try to explain what's going on. All right, so the first thing, we know that for a sine function, no matter what sine is, no matter what's inside this sine function here, we know that sine bounces in between -1 and 1. We already know that, okay? We also know that sine is an odd function. So here we know that sine of theta is going to bounce in between -1 and 1, no matter what theta actually is. So let's say if we let theta equal this, okay? Now, the issue here is how theta is actually acting. And so with this sine part, all this is going to do is limit how far up and how far down this particular function is going to go. And we actually saw that when we were looking at both the graph of sine of pi divided by x in Desmos, as well as in the TI-84 graphing calculator. Okay. Now we haven't learned this yet, but there is a limit law, I should say limit corollary, that says that for functions like this, a way that we can actually look at this is we can actually slide this limit operator on the inside here. And again, I'm kind of going ahead here just so that I can actually try to explain what's going on. Okay. Now, remember sine, all this is doing is whatever's inside of here is limiting that the highest it could be is +1, lowest it could be is -1. That's the role that it plays. So my point here is that if I really want to figure out what is going on behavior-wise for this particular function, I'm going to have to study the behavior of the inside function for it. Now, if I was to draw the graph of pi divided by x, notice that pi divided by x is the same as pi times 1/x. which is just basically a graph of 1 over x, our basic reciprocal function, and is going to be vertically stretched by a factor of pi. In general, this graph looks like this. And of course, we have a vertical asymptote here at x equals 0. Okay. Now, the values that are inside of this sine function here are acting like this graph. And of course, as x approaches 0 from the right, do you notice how they get, how these values here get more and more and more positive? Okay, so they're getting bigger and bigger and bigger. Here, they're getting more and more and more negative. And so notice here that the graph of this function, if I looked at the limit as x approaches 0 for this graph, I would have to answer it as does not exist. And why is that? Well, for the limit of a function to exist, one of the things that we have is we have to have the behavior of that function be the same coming from both the right of the number that we're talking about as well as the left of the number that we're talking about. So that means that the behavior of this function will have to be going in the same direction, and on top of that, what that direction has to culminate in is a y value that's a real number. Okay. In this situation, I have a problem because the behavior of my graph as x approaches 0 from the left goes down to negative infinity. As x approaches 0 from the right, the behavior goes up to positive infinity. So for that reason, it does not exist at all. Okay. Now, if I had something like limit as x approaches 0 of pi divided by x squared, then the graph of this function would look something more along the lines of this, where again I still have a vertical asymptote here at x equals 0. Okay. Now, in this sense, the limit of this particular function here would actually end up being infinity. Okay, because we see as x approaches 0 from both the left and the right, we see that the y values just keep getting bigger and bigger and bigger in a positive sense. Now, even in this case, even though the limit goes to infinity, it does not mean that the limit exists. Because remember, if a limit exists, there's two things that has to happen. One, the behavior of the function as x approaches whatever value that we're trying to do has to be the same from both the left and the right. And on top of that, whatever it's approaching, it has to approach a real number y value. And of course, infinity is not a real number value. It's a concept, but it is actually not a number. Okay. And so for that reason, even though we would say the limit of a function like this would approach infinity, technically speaking, this is still a does not exist case. Okay. However, we reserve the DNE does not exist case for situations like this one where the behavior from one side doesn't even coincide with the behavior from the other side. Okay. Well, as for here, the behavior is the same, but it's still not approaching a real number, a fixed, distinct real number. So remember the point about limits is to describe behavior. This is the best way to describe the behavior, to say that it goes up to infinity for this particular limit. But if we say does a limit exist, we still have to say no. And so the stuff that I'm showing you now comes from that primer of limits video that I told you about earlier in this video. So hopefully now you see how we could have really just looked at this and use mathematical context clues, as I like to call them, and say, hey, sine just limits me in between -1 and 1. This inside function here, if I take the limit of that, is acting like this reciprocal function here, and I know that behavior from the right isn't the same as the behavior from the left, so the limit has to be a does not exist case. And that's why it ends up actually being. All right, so the next function that we had was just basically a piecewise function where h of t was equal to 0 as long as t is greater than 0 and is equal to 1 if t is less than or equal to 0. And so I have those two pieces of the piecewise function here. All we're going to do now is just get it into a viewing window that is acceptable. So here we need to be able to see the 1 at least here. So I'm going to do my x min here to be -2 to 2 here, and x max will be 2. Our y min will make that be a -0.5, and our y max, we will allow that to be 1.5. And so we see here for this particular piece of the piecewise function, this is the piece where y is equal to 1, values of t less than or equal to 0, and then of course for values y is 0 for values of t greater than 0 here. Now, if we click and scroll, we see that as x approaches 0 from the left, it's going to be approaching a y value of 1. But if we do the same thing from the right, it's going to be approaching a y value of 0. And like I mentioned before, if the behavior from the left isn't the same as the behavior from the right, then by definition, we have to say that the limit does not exist. So for this piecewise function here, if we wanted to say, well, hey, what's the limit of this piecewise function? Well, it has to be does not exist if it's approaching, in this case, t equals 0 from both the left and the right. All right, so now let's look at this graph. This is a square reciprocal function that is shifted 2 units to the left. And this is one of those graphs that you should know how to just sketch, by memory from pre-cal. But I'm going to go ahead and put it in a viewing window. That'll be a little bit more conducive to what we're trying to do here. So we'll say -10 here, 10 here for the x min and max. And I'll do the same thing for the y min and y max. Okay. So in general, this is how this graph looks. I'll pull it down a little more. As we discussed earlier, in this case, we see as x approaches -2, because for this particular one, we wanted to know what was the limit as x approaches -2 from both the left and the right. Well, here is -2 right here. So as x approaches -2 from the left, we see that the y values keep on getting more positive. As x approaches -2 from the right, y values get more and more positive. So the limit to this particular function as x approaches -2 from both the left and the right, it will be approaching infinity. So that is how we answer the question for the limit, because remember, limit means behavior. However, if we say, does the limit of this particular function exist at x equals -2, we still have to say no, because infinity is not a real number, okay? All right, and so for our last one here, we're going to look at the graph of y is equal to x squared minus 25 divided by x minus 5, okay? Now, for this one, if we algebraically look at this, notice that x squared minus 5 has a factor of x minus 5 in it, okay? So what we're really doing here is looking at a graph of what's left, which is the graph of x plus 5, but we're going to have a hole in the location of where x is equal to 5, Okay. And so that's essentially what this graph is trying to show you here. I'm going to zoom out just a little bit. Now, if we trace this, notice that the closer we get to 5, of course, when x is 5, this looks like the y value is going to 10. But when we actually get there to 5, do you see how it's undefined? Okay. And so that's what it should be, because if I plug in 5 here, I'm going to have 0 in the denominator. Okay. But we see as x approaches 5 from the left, it's getting closer and closer to 10. As x approaches 0 from the right, it's getting closer and closer to 10. And when we actually get at x equals 5, even though the function itself is undefined, the behavior of the function is still approaching a y value of 10. And so that's the reason why this particular rational function here, its behavior or limit as x approaches 5 from both the left and the right will be 10. All right, so now that we've looked at all of these functions here, we know that the limit for this particular one here is going to be does not exist. We know that the answer to the limit for this one is going to be infinity, but technically the limit still doesn't exist as well, because it's not a real number, but we answer it with infinity. And of course, the limit for this particular function here ends up being 10. And so this concludes the video on looking at limits empirically. I hope this helps. Take care.